We have to talk about, we weren't completely done with chapter 5 with molecular orbital theory. So let's talk about interactions between molecules. And then we'll lead off the rest of today into solid state stuff. So this is probably the only time in your academic career that you're going to ever talk about solid state. It's a really cool area. I did a lot of graduate work relating to solid states, so I looked at surfaces, so it has a special place in my heart. But it's really kind of the realm of physics right now. And the reason for that is it's just for historical reasons. Tend to be that chemists would focus on gases and physicists started focusing on surfaces and solids. And now we're getting to the point where chemistry is starting to trickle into talking about solids. Does anybody really know why? Like all things, it's ruled by money. Pharmaceutical companies are, if they get a crystal structure of whatever they're looking at, they can generate a lot of money through patents that way. There was actually an AIDS drug where there were 2 types of crystals. They patented one of the crystal structures. They didn't get the other one. And that other one was actually the active one. And they lost out on literally billions of dollars because of it. So, yep, makes a pretty potential impact. That and we're starting to have experimental techniques and theoretical techniques where we can look and investigate these systems. Physicists tend to come up with all the forms of spectroscopy and then they go, okay, it worked for, spherical balls in a vacuum, and then chemists start to apply it to real world things. We're thankful to the physicists for coming up with this stuff, and we tend to use it. Before we get there though, we have to finish up with chapter 5. So let's talk about MO interactions. Between molecules. And this is going to be important for us when so we're going to skip over chapter 6, we're going to go back to it. But this is really where we start talking about the acid-base behavior, using molecular orbital theory to talk about that. So the majority of electronic interactions, they happen it's usually the overlap between frontier orbitals that causes this. So, frontier orbital, different molecules. Interact. So, and what do I mean by frontier orbitals? Does anybody know?
That's kind of one too.
Yeah, it's kind of come one too. It's kind of, we talked about them, but we never called them frontier molecular orbitals in this class. Or which ones do you think we always, so in all those diagrams, I made you point out two. Yep, the HOMO and LUMO. It's usually the HOMO and LUMO or states around the HOMO. So we're going to consider the frontier orbitals. That's just going to be HOMO and LUMO. Some people define that as other states beyond those, like some that are just close to the HOMO and LUMO. But for our purposes, we're going to just say those two. So let's look at charge transfer interactions. So we're going to look at 2 hypothetical molecules. We're going to have molecule A and molecule B. So we have molecule A, molecule B, and then when they interact with one another. AB. And so we have an occupied state on A, and an unoccupied state on A also. So this will be our, actually we'll put it over on this other side. Well, there are other states beyond these, but these are just the 2 that we care about on A. Then we'll have HOMO on B, and then we'll put the LUMO up here. And then we're going to have that interaction. So there's something that's going to happen in between here. There's going to be overlap between some of these orbitals. Okay, in order for there to be overlap, so these molecular orbitals are going to overlap and we're going to get new hybrid orbitals. What do we have to keep in mind for the new orbitals that get constructed? What are the things that we have to consider? Or which of these are going to interact with one another? Or which ones do you think are going to interact with one another?
Lumo of A, lumo of B,
Okay, why?
because they're close in energy.
Yep. So close in energy orbitals interact. What's another thing that we have to consider besides energy?
There must be the same number.
Oh yeah, we have to have the same number of resulting molecular orbitals. That's true. What else besides? So if we're looking at orbitals that interact, what else besides energy do we have to consider? There's one other big important thing that we talked about in chapter 4 a ton. Starts with an S.
Ends in
Geometry.
the.
Yep. So the symmetry of these orbitals is also important. They don't have the same type of symmetry, it's not going to work out. Okay, so you're right. So the HOMO of B interacts with the LUMO of A. We'll get a new interaction in that way. I'm just going to leave it right there. So these are new hybrid orbitals. We're also going to have that guy there that remains relatively non-bonding, and then we'll have another one up here that's non-bonding. Okay. So now this gets occupied, right? Okay, which way is the charge transfer going? Is it going from A to B or B to A?
B to A.
Yep. Charge from B to A. Why did you say that, Kinsey?
A is the lower electronegativity, or higher electronegativity.
We're gonna leave electronegativity out of it for right now.
Then I don't know why I said that.
Okay. If we were talking about atoms, you'd be correct. In this case, since these are both molecules, it's a little bit different. Okay. Are there any electrons occupying this orbital? No. But they were occupying this HOMO, right? So now when these two overlap, some electron density is going to go from B's HOMO to A's LUMO, right? So now, this was once completely unoccupied. There are now some electrons occupying it. So there's charge transfer going that way. Does that make sense? Okay. You might be asking, like, what is this an example of? We could consider, we're going to do this again in chapter, after we talk about solid state stuff, but if you were to consider BF3, and then ammonia, so the interaction between those two, would you think those two would react? You might not, because if you look at them, everything's happy, charge is good, but they do react. What ends up happening is these two electrons go there, and then we get this weird looking compound. And wherever there are two electrons donated like that, that's called a dative bond. I'm forgetting one more thing on here. What am I forgetting?
Charge.
Yep, what's going to be the charge on that boron?
Positive. Negative.
Yep, negative. And then this guy's positive, right? Nitrogen doesn't want to really have four bonds. Okay, so in this case, which one's acting like A and which one's acting like B?
That's the nitrogen.
Yep, so the ammonia is B, the boron trifluoride is A. Yep. Okay, and we can have the same kind of interaction, it just could be opposite if we wanted to. There's also one more interaction that really is unfavorable for molecules. So sometimes molecules don't or have the best interaction that way. So let's talk about repulsive interactions. And this kind of has to deal with the question when I was asking about the helium dimer on the exam, why it was unfavorable. Okay, so what we're going to do here, we're going to have same thing, energy on our axis, which I didn't label on this one, Shane. There we go. We'll have A, we'll have B. And I'm leaving off all the other energetic states for A and B, just considering how I'll open them up. Okay, which of these orbitals are going to interact, do you think? Yeah, we'll look at the two homos. The two LUMOs might also do it, but let's say these guys have the same symmetry and they have similar energies. So they overlap. We got A here. Okay, so these fill up, right? What has happened to the bond order of this system? Is it increased, decreased, or not changed?
As compared to that one?
Yeah, well, as compared to, like, let's say, looking at these two molecules, is there an attraction between A and B right now? You're saying no. Why no, Mariah?
Because everything's kind of like the same. Like, it's not really, there's no energy really change.
Can you be a little more descriptive than that?
Like on this one, like it wants to go to like blue because there's like an energy exchange. But this one, they're like at the same like energy level.
Okay, I see what you're saying. No, that can even if they were the same energy, like let's say if this homo and that LUMO were the same energy, there would still be an overall attractive interaction between the two. So that's not exactly why. What type of orbital is this?
Bonding?
Bonding. What type of orbital is that one? Anti-bonding. So if we look at those, is the bond? What's the bond order if we look at that? Yeah, 0. So it's not really increasing the bond order at all. This is actually a repulsive interaction because we filled both the bonding and anti-bonding. Now these electrons, they're occupying almost the same space, right? Do electrons want to be near one another? No, they're going to repel one another, and this is going to cause a repulsion. And this is what is known as Pauli repulsion. So the bond order, bond order is equal to 0, and these guys repel due to Pauli repulsion. So the electrons don't like to be near one another, they separate, and it causes the molecules to move away from one another. If A and B start to move away from one another, what happens to these energy levels? So are they gonna, is the energy difference gonna increase, or what's gonna happen if they move away from one another? Or the overlap gets worse, right? If they move further away.
Overlap is worse, that's a weaker bond.
Right, so what's gonna happen is they're gonna go like this, and it's essentially gonna look like a non-bonding interaction. Okay? We're gonna review those kind of concepts when we go back to talking about acids and bases, but if you have an idea of this already, it's gonna make that discussion a bit easier. Okay. Are there any questions about that? No? All right, we're gonna go into a completely different area, probably one that you hadn't talked about much since general chemistry. So all about solid state stuff. And in general chemistry, do you remember much about solid state things at all? Not a ton? Do you remember crystal structures or anything like that? Like,
Oh yeah, the different kinds.
yeah, there are different kinds, and you probably talked about like cubic,
Yeah.
body-centered cubic, face-centered cubic. And those are the ones that you typically focus on because they're the easiest to see. However, there are a variety of different crystal structures that you can have. But we'll get there in a second. So this is all in chapter 7. This is about the solid state. So we're going to use part of chapter 7 and the Hoffman handout that I gave you guys to talk about. So there are really two classifications of solids. Do you know what they are? So what's the one that you studied in Gen Chem? Yeah, what did you say? Yeah, crystals. We have crystals. And what is a crystal?
Isn't it uniform?
Yep, it's uniform, so there's usually a unit cell. So we're going to say it's ordered, repeated units, and if there's order, what are we really talking about? Like, okay, so have you ever heard of the artist M.C. Escher?
Yeah.
Yeah? Do you know any of his paintings or,
No, but
like, could you describe what you've heard of him at least,
Yeah.
right?
Yeah.
Okay. So let's,
Are those ones that have like the same thing over and over again?
Yep.
Right? Yeah. Okay.
and those are called tessellations. Let's try and find a good one. I like this.
They're like different patterns. They're like interwoven and they're the same
Yep.
thing over and over and over again.
My parents have one of these in their bathroom, and I did, like, every time I go in it, I just stare at it. Oh, Pinterest, no! Hate Pinterest. They want to make you register for everything. That's all I'm getting along here. Okay. This is actually one I use in Gen Chem. Rippled surface. Ooh, that's cool. Let's go with reptiles. There we go. Okay. So we'll pull this up quick and turn down the lights. Shut this door. So, this is an example of a wallpaper group or one that has two-dimensional symmetry. So we have repeat units, and then we also have different symmetries that are hidden in here. And when we want to draw a unit cell, we have to connect certain points where we want to keep that repeat unit constantly going. Let's pick a little bit easier one to go with to start. Let's try Pegasus. That one's a bit easier to see the crystal or the unit cell. Can anyone go up there and draw one with their hand where you see a repeat unit? There are a bunch of them that are up there right now, but anyone willing to go up there and just draw with their hands where one is?
I think I saw it better with the other one.
Wait,
Did
you're
you?
talking about the horses?
Yeah, just the horses. So if you were to take a cut of this, like a smallest representation of it, and then copy that in all directions, would you get the same image?
Yeah.
Yeah. So could you draw the spot you would cut out, and then if you had to just keep copying and paste that?
Would it just be 2 horses?
Yeah, show me. I want to see it. Let's see if you know.
Pick a white horse and a red horse.
Yeah, just go up there. I just want to see you draw it.
You got it.
Oh, no, something like this. Like in here and then.
Oh you could get real intricate like that if you wanted to. I was even talking more simplistic.
Like a square.
Yeah, like if you start at this eye, go
Oh,
there,
yeah, I
there.
can't do that.
Oh, Actually, there.
The other ones look like hexagons to me.
There we go, like that. That's an example of one. You can pick a couple different ones though, right?
Yeah.
So the other one, do you like the other one better?
I think so.
I don't know if I can see that one. Let's try.
You can see the hexagons.
Yeah, I hate hexagonal networks.
You see
They're
it?
evil. I don't know. Let's,
I can see it.
Yep. But we want to make sure that the color is repeated too. Like, see how this one, like, so if we copy that
okay.
over, this one's a little more difficult. So we would have to get like,
All the colors.
yeah, we'd have to get all of them. So we'd have to like draw.
I think it's like
Excel
3
that way.
hexagons then.
Yeah, hexagonal networks are annoying because, I don't know, I think in squares. I usually don't think in hexagons or triangles. Let's see if we can't find another one. Fish! No, that one's. The ones with color are annoying. Butterfly?
Oh.
Ooh, that one's pretty. But you can sort of see that symmetry that's in there in that repeat. Yeah, this one, if we don't include the yellow, it's pretty easy. Can you get the squares? I don't know. But you can see that sort of symmetry that's there. And they actually have wallpaper groups, so like our point groups, to show each type of symmetry. And somebody went through and decided, okay, these are the symmetry groups of all of Escher's paintings. And then there are crystal structures that they use to go along with it. So
God bless.
as complicated as 2D is, imagine trying to do this in 3 dimensions, which is where we're going to get to. We're not going to talk about a bunch of them, but that's what people do. And those are called space groups. So, but for now, we'll leave that off. We'll go back to this in a little bit. So, we have ones that have repeat units with symmetry. So that's one classification of solids we can have, is repeat units with symmetry. And we have one more classification of solids. What do you think the other one is?
Doesn't repeat, mostly.
Yep, doesn't repeat. Not ordered. And limited symmetry. Does anybody know what kind of system that is? Known as amorphous. Sorry, what was that?
Yeah, we went over like the crystal, like usually like Bravis slow and like the bigger,
What is that?
more.
What class is this?
I was thinking analytical.
I think.
Oh, maybe you did.
I think we did because we went over like how like more pure it is, the bigger it is.
Okay. Oh, like the crystal itself.
Yeah.
Okay. Did you guys talk about like X-ray crystallography at all?
Oh.
Or-
I think so, yeah. But I don't really remember much about it.
It's a complicated system. People used to get, they'd have to take Polaroid pictures of like little dots, do a bunch of math and try and figure out what these crystal structures look like.
I think we could do that.
Now you can buy a unit the size of like that box there, plunk something in and you'll get a crystal structure now. So it's like nothing. Maybe we'll go to Fredonia. So Fredonia has like a high-end diffractometer, which maybe we'll go check it out at some point as a field trip or something. So out of these two though, there are a lot of amorphous systems, but they're difficult to study because they're not the same throughout. We're gonna focus on just crystals for now. So we'll focus on crystals. And the main reason for that is they're much easier to study, and we have a lot of experimental techniques that can look at crystals, and a lot of theoretical techniques that can look at crystals. So I think in modern physics, didn't you guys do something where you looked at a powder diffraction pattern of like sodium chloride? You had to try and be out of Dr. Pianka, and no one did.
Probably not.
Which I'm surprised, he's a theoretician, he should be bad at all that.
Oh no, he's very good at it. He's good at epic things, okay?
He's great at everything. So unit cells, so we drew a couple of them out there, but what these are, they're just the repeat unit and a solid. And symmetry is denoted by a space group. So in chapter 4, we talked a ton about symmetry and we talked about point groups. What didn't change in a point group? Like, why does it have that name, point group? So every time we did a symmetry operation that worked out, there's one thing that didn't change.
That first axis?
Yep, that first axis, the principal axis, right? And if you look at like water, we had HA and we had HB. There's a C2 that goes along like through the dead center, right? So here's our C2. When we did that, which of these elements didn't, or which of these atoms didn't change positions? The oxygen. So in point groups, there's one point that doesn't change. Now space groups, what do you think is not changing there?
Space.
Yep, space. Because now we're talking about 3 dimensions, and we can't really talk about a single point because when we consider a crystalline solid, we pretend it extends throughout infinity. It doesn't, there are ends to it, but for the bulk of the material, it just repeats constantly. So we denote this through a space group, so the space isn't changing. Space does not change. Which is good, so we can categorize things based upon this. But what's the downside to this, you know?
Probably hard.
It is really hard, because you have to think in 3 dimensions, and there's a lot more symmetry operations beyond what we talked about. So, like for example, there are things called screw axes, where, like if it starts off at a point here, you rotate it. So if this was in 3 dimensions, you rotate it, there's actually a bit of symmetry that's here. We've never discussed those. I'm not planning on discussing those, but there are other operations beyond what we know from point groups. The other downside is right now there are 230 differently known space groups. So there are 230 different space groups, which makes knowing a specific space group much more difficult. Like everybody kind of has a molecule in their mind when I say like D2H or C2V, like C2V, you think of water, C3V, you think of ammonia. But if I were to be like PMNA, some people would be, then that's the way that they write space groups. They would be like, all right, first, what type of crystal lattice are we talking about? This, I don't even know. I don't remember off the top of my head. I forgot all that stuff. I took a crystallography course from one of the main guys who came up with most of it. There were 2 professional crystallographers in the class. They failed. Me and one other guy got a B. He said that was awesome because that's one of the highest grades he's ever given. Me and Mike Gross, we were like, oh my God, that was the hardest class I've ever taken in my entire life. It was fun. I would suggest to do it, but I would audit the class. So, but each of these means that, like this one, there's a mirror plane, this one's a symmetry plane, this one means that there's a glide plane. Those don't mean anything to you, but unless you're a trained crystallographer and you know exactly what space group you're talking about, everybody else probably doesn't know what you're discussing. So it becomes difficult and taxing. But we're going to take a little bit of an easier approach. We're not going to focus on all of those complete symmetries and space groups. We're going to focus on something called the Bravis lattices. So it is easier to identify the Bravis lattice. And most people in chemistry and definitely in physics know all the Bravis lattices. There are only 14 of them. Okay. And these don't include all the different symmetry aspects you can have to a crystal. Now, how do you identify the Bravis lattices? So to determine these, you have to look at the unit cell lengths. So you need to look at unit cell lengths. So we're going to try to draw a crystal, a three-dimensional crystal. We're going to try to go cubic to make our lives easier. Okay. We'll try to label these with different colors so they come out a bit different. So we're going to call this axis along here, that'll be A. Oh, the kind of depth going in will be B, and the axis going up is C. So we can have a couple different options here. We can have different lengths of A, B, and C, so those different axes, right? What else could be different between unit cells or crystal cells? Or what else could we change with that box? Yeah, what's in it, like the number of atoms, which we'll talk about it. So we need to look at the number of atoms. So number of atoms in the cell. What other things could we change? I said we started with a simple system of a box, right? Or a cube.
You should change the shape of the
Yep.
size.
Yep, the shape or the angles. So depending on how some people may define these, they may call this one alpha, beta, or gamma. Really depends on your coordinate system. But the angles between each of what's called the lattice vectors, or A, B, and C. So look at the unit cell. And that's how you can figure out what the Bravis lattice is. Okay. And there's a little table in your book. We're going to pull it. It's figure 7-1. We're going to pull them up on here though. Let's try to get a good picture. That's fuzzy. That's. Yeah, but it doesn't list all of them. Oh. So you want to look at figure 7-1 to see in your books to see what these look like, but we're going to pull them up real quick. So they fall in several crystal classes. So they're cubic, tetragonal, orthorhombic, rhombohedral, monoclinic, triclinic, and we're missing hexagonal, which is annoying, so I'm going to try to find. Actually, that one looks better.
Did you say 7.1?
7.1, I think it is. Okay, this might be a better picture. There we go. And you can see that they're kind of defined by their unit cell lengths, so A, B, and C. So for cubic, all the lengths are equivalent, all the angles are 90 degrees. However, if we go to something like triclinic, we have all the bond lengths are different. None of the angles are equivalent or equal to 90 degrees. So which of these would you suspect to have be higher symmetry or have a higher amount of symmetry, and which of these would you expect to have the lowest amounts of symmetry? Or which one do you think is going to usually have the least amount of symmetry out of all of these groups? Yep, triclinic, because nothing matches, right? What would be, I don't know, another one that would be kind of low symmetry? Yep, monoclinic. And then these other guys, it's questionable or debatable what's in there. Okay, so wherever you see the blue groups, those are P, that's for primitive. That means if you go on just like the perimeter edges of your unit cell, you have an atom that's there. The eyes, I don't know why they picked eye for body-centered, but it's there. So that's where there's just one atom kind of hanging out in the center of the unit cell. Face-centered, there are atoms along the faces. C, side-centered, that's only for orthorhombic and monoclinic ones, but that's where one of the sides just has an atom hanging out at it. Okay? Now, if you go into the chemistry offices, you'll see that there are a ton of these crystals hanging around. You guys are going to have an assignment. What I want you to do is I want you to take pictures of the listed crystal cells, the Bravis lattices that I have. You can either print them out or you can send them to me, but there has to be a label for each of them, okay? So I just want you to go through, look at them, determine which ones we have. So you're looking for a face-centered cubic, a hexagonal, a tetragonal bodied center, a triclinic, and a monoclinic. Does everybody have the book or no? Okay, if you don't have the book, you can always come borrow it from me. This website along here, that's probably going to be a good spot to go to because you can sort of see these. The things that you really want to start to look for, you want to check the lengths first, then kind of look at the angles, then consider the number of atoms that are in there. The models that we have sometimes...
Did you say length and what?
Length, angles, number of atoms. Some of the models that we have in there can be pretty tricky. They aren't just one unit cell. Sometimes they have more than one unit cell. In case of hexagonal, this is like a little cut that's out, but if you smack it around, you can get something that looks a little bit different. So like, let's get...
Could you explain the difference between side-centered and face-centered?
Yes, so face-centered, in a face-centered cell, if you look at these guys, there's one atom at every face.
Oh, it has to be every? Okay.
Yep, where side-centered, it might be just two faces.
That makes sense.
Sometimes I think it's even four faces, but we'll leave it that way. And then if you look at a hexagonal cell, this is a good example here. If you look back, we just indicated a little slice of that. That's what's on this picture here, kind of in the blue. But you might find in the model that has all of that there, and it gives you more of that hexagonal look. And that's why it has that name. So it just depends on the definition, the way people set them up. If you go through and look at the crystal cells, you should be able to find some information out that way. Okay? Are there any questions about that classroom assignment? No?
Wait, when's this due?
Next week, next Thursday. Is that enough time, do you guys think? Okay. I'll give James some time when he comes back. Yeah, so that's really all I'm gonna expect you guys to know, and probably if you go on somewhere, that's all you'll really be expected to know about crystal cells. If you're a geology major, they have to know like every space group and be able to identify them, so be thankful you're not a geologist, because there's a lot of minerals that have a bunch of different types of symmetry. Okay, we'll blank this for now, we're gonna need it in a minute. Throw that up. And then we're going to talk just just really shortly about hexagonal close packing cells and co-crystals for a minute. There we go. Okay, so did you guys talk much about hexagonal close packing cells in Gen Chem? Where it was like a bunch of orbs and it's like, what is the most effective way to pack a bunch of spheres? Did you ever really talk about that? Okay, that's all right. I kind of think it's a waste of time in general chemistry to talk about because the only people who use it are chemists and physicists for the most part. But there's different kinds of stacking you can have for hexagonal cells. So we're going to talk about the close-packed structures. So what we're talking about is okay, how can we organize atoms? So the most efficient packing of spheres. So the roots of this are kind of interesting. They came from a military aspect on trying to consider packing these spheres. Why do you think the military cares about that?
Lighter. Get things lighter.
Yeah, get things lighter, it's more efficient, you got the whole hoorah attitude of like it's done, it's out of the way. But why were they focused on spheres? It's kind of more old-timey. Not just bombs, but yeah, cannonballs. They wanted to know how most effectively to pack cannonballs together so that way they could transport them easy. And what they found was you could do some sort of different types of packing together. So like if each of these are the spheres, we could do something like this, right? And then we'll move that one back. And we would pack them like that, right? There's another way we could approach this though too. Let's try to draw it. I hope it doesn't come out looking the same. It's gonna come out looking the same. All right, let me retry that one. They look almost the same, don't they?
What are you changing?
I'm trying to move the angle.
So you're trying to make it more like Bravis?
That, yeah. That looks a bit better.
Yeah, I see what you're doing. Instead of bringing the next row back.
Yeah. So like, if you think about the stanza of a poem, like you could have different flows, right? There's like A, B, C, there's A, B, A, there's A, B, C, D, and that, right? So what I'm trying to go for here is like this is A, that's B, that's A. Whereas this one's A, this one's B, this one's C. The book does a way better job of drawing these, and especially in 3 dimensions. So what these are, they're different ways of packing these spheres. So they wanted to try and, they found that this was the most efficient way to pack these guys. Way later on, when they started looking at how atoms arrange themselves, they found that a lot of structures tend to do this. Nature wants to pack most effectively, it's going to try and do it that way. So this is what's known as hexagonal closed packing. Packed. Sometimes the HCP is sometimes what it is. And then this one's considered face centered. And we have cubic close centered, or close packing. So this one is CCP, and this is SCFCP. And they tend to just have this sort of stacking arrangement where these two are in the same X and Y region, but they are, they just have different heights. So we'll try to color in these to show that there's a difference between them and this one. That they're just sort of different layers that are in there. Most metals, a lot of metals like copper, silver, and gold, they all do this sort of hexagonal close packing arrangement. When you look at different faces, when you look at graphene, I think it can have either of these two different arrangements. So that's something you might see later on. All right. Now back to that whole AIDS drug that we were talking about at the beginning. There is another form of crystals that you can have beyond just having a single atom or a single molecule in there. You can actually have what's called co-crystals. You guys have seen these before, but they probably weren't called co-crystals at the time. So co-crystals. There is a wide debate on the definition of a co-crystal. So what I tell you here today might not be the same thing. From what I looked at, I U-packed a bunch of old guys that sit around and decide what everyone's going to call everything in chemistry. They haven't agreed upon this yet. So definition is variable. However, I know some researchers in this area, and what they would most likely say, one of the guys I know is super anal retentive, and you probably have a big to-do about it. He works for the government now. I can't say his name because he might be classified. This will be on YouTube. We gotta watch out. Anyone sit there, yeah, you say anyone do that? We call them the princess of the lab, though. So, so it's where you have two or more molecular entities that combine together to make a crystal. So two or more molecular entities that form a crystal. So you have two molecules, they aren't reacting with one another, but they just assemble into a certain pattern. You guys already know some of these. And he talked about them in Gen Chem. I'm pretty sure. They're probably the most annoying to name. For example, I think it's, do you remember what those are called? Or what does that dot mean?
It's like not wanted, but it's like there or something.
Yeah, exactly. It's incorporated into the crystal lattice, and it's just sort of hanging out there. This is known as a hydrate. So you've probably seen it before. If not, we'll bring some in where we'll take, so do you know what color copper sulfate is?
Blue.
Yep, it's blue, and you can take some heat to it, and it usually has water complex to it. So the hydrate is a blue color. You can get the anhydride where you take out all the water and it's this ugly white chalky looking thing. And luckily, well, good or bad, we live in a humid environment where if we left that out, eventually it would turn into copper sulfate. If you actually leave that out for a while, it'll dissolve itself into a solution. So if you leave some solid copper sulfate out and come back in like a year, you'll have a solution of copper sulfate.
That's nice.
Yeah, it's fun. Total pain in the butt for this area. So like when we go into the storage room, we have to make sure everything's parafilm, things are dry, or in desiccators. Because sometimes the desiccant goes bad, then we lose a bunch of stuff that way.
So like if you're like out west, does it happen less often?
Yes,
It's
much
so
less
dry.
often. Yep, so like where Dr. DeVue went, where it's nice and dry and happy all the time, he probably doesn't have any issues where they're storing their chemicals. However, here, it's a big deal because the air humidity is just so high. Even in the wintertime, it can be rough. So that's why we all, like when they rebuilt the new Walsh Science Center, we wanted a climate-controlled stock room We didn't exactly get that, but that's why we wanted
Did
it.
they think that they got it?
I mean, it behaves okay over there, but sometimes it's just really hot and sometimes it's just really cold. It's not as climate controlled as I would like,
Or
but
just like, family, that's temperature
Yep.
all day?
yep, exactly. That's temperature and that's the humidity. So we have a temperature control, but we don't have necessarily a humidity control, which also drives me nuts because of like the cluster that we have in there. You don't want a lot of, you want it to be cold in there and you don't want it to, be wet. It's not the way. Same thing with the NMR room. It's just in flux. It should be temperature controlled, but. So, so Kinsey, you were saying that the water molecules are just sort of there, right? They're not bonded to anything, they can be pulled out. So let's try to look at one of these crystal lattices that's like this. So let's try hydrate crystal. That's weird. Ooh. All right, there we go. Is it? Taking forever. That's what I want. I want to get a big picture of that. All right, that wasn't useful. Okay, we're going to move to a different type of compounds that are much easier to see. Have you guys ever talked about clathrates at all?
That sounds really familiar.
Okay, so clathrates are pretty cool, where what they are is a molecule that will, this is actually a really good example. So you have water that's sort of hanging around and then it will trap molecules in its crystal lattice. So this is a methane clathrate and it's, no one's ever seen those or played around with those before, right? Okay, they're cool because you can actually make ice catch on fire. So if you go close to like where, under the ocean or in the ocean, to go to really deep depths, you'll actually find that some methane gets trapped in these and then light it on fire. So let's see, methane, ice.